Hi everyone. So today we are going to talk about another topic, very important topic in algebra and pre-calculus, combining functions. In the previous lectures, you are now familiar with what is the meaning of a function, what is the domain and range of a function, and now it's time to go one step ahead and understand what does it mean by combining functions. So let's get started. So let's first try to understand the meaning of combining functions. What does it mean actually? So say I have two numbers, say 2 and 3. What are the ways I can combine them? That means in what ways I can do some algebra with them. We can add the numbers, we can subtract the numbers, we can multiply the numbers, and we can divide them. So these are the four fundamental elementary algebraic operations which we can do with numbers. Now, the same thing can be done with functions as well. We can do the similar operations on functions. So say you have two functions, f of x and g of x. So in how many ways you can combine them? So one of the ways is to add them and produce a new function, fx plus gx. Similarly, because when you were adding numbers, so when you added them, you produced a new number. So in functions also, you produce a new function when you add two given functions. So this new function is known as the sum function. And these are the two ways it can be denoted. You can write f plus g together and then the argument x, but it actually simplifies to fx plus gx. And similarly, we can subtract two functions, f minus gx. We can multiply them, fx times gx, which is f times g operated on x. We can divide two functions, fx divided by gx, also denoted by f divided by g at x. And in sum, you can understand it won't really matter whether you do f plus g or g plus f, because similarly in numbers we have the same thing, right? Whether you do 2 plus 3 or you do 3 plus 2, you get the same output. However, in subtraction, if you change the order, you get a different number. Similarly, in functions, if you do f minus g and you do g minus f, you do switch their order. In subtraction, they are different functions. Multiplication, it stays the same. 2 times 3 is same as 3 times 2. So f times g is same as g times f. And division, of course, is different. 2 over 3 is not same as 3 over 2. Similarly, f over g is not same as g over f. So these are the few fundamental definitions of four types of combination of functions, which we call sum, difference, product, and quotient. So this is the formal definition. I would say practically the same thing which I wrote, but written in a more detailed way. So sum is f plus g, difference is f minus g, product is f times g, fx times gx, quotient is f over g, which is fx over gx. Now, if you read this, what does it mean? Provided that gx is not equals to 0. So there was no extra condition in any of these, sum, difference, product. However, for quotient function to be a well-defined function, we do have an extra restriction that the denominator cannot be 0. This comes from the fundamental mathematical fact that you cannot really divide by 0. So denominator is not allowed to be 0. So this function will be a valid function, a well-defined function, only at those points where the denominator function is non-zero. So you always have to be a little extra careful with the quotient function that brings along additional restrictions, but we are fine with sum, difference, and product. So these are the definitions, and now let's see how we use them in an example. So first I can give you some simple example. Say f of x is 2 and g of x is x plus 1. So since this is the first example, this is very simple. I have taken one of the function to be just a constant function, right? You can see it's just a constant function, and this one is a linear function. You don't need to go into their nomenclature. You don't need to go in that direction that identify what function it is. Rather, you can just directly go with the operations. But it's always good to know functions or recognize them with their names to understand them better. All right. So what would be sum function here? So sum function is f plus gx. So I would say this is the definition. But how it is implemented, like how do you actually perform the sum into functions? You're actually adding the outputs, because x is the input, fx is the output generated by f function, gx is the output generated by g function. So you simply replace fx with its value, gx with its value. So fx is 2, gx is x plus 1, it is here. So it's 2 plus x plus 1. Of course, you can simplify that to x plus 3, because that's a general rule work for every algebraic expression. We can always combine like terms, x terms with x terms, constants with constants, and so on. So yeah, that's the sum function, x plus 3. What would be difference function? F minus gx is fx minus gx. So fx is 2 minus, now gx is x plus 1. So make sure you put a parenthesis here, otherwise you'll end up getting the wrong answer, because the whole function has to be subtracted. So make sure you first put parentheses and then simplify it. So it would be 2 minus x minus 1, and if you now combine constants, so it's negative x, 2 minus 1 is plus 1. And then product is f times g, which is nothing but fx times gx. Fx is 2, gx is x plus 1. So when you multiply that, so 2 is going to be multiplied with x, and then 2 is going to be multiplied with 1, gives you 2. So 2x plus 2, that's the product function. And then if you talk about quotient function, so that's f over g. So fx divided by gx. Fx is 2, gx is x plus 1. That's what you get as a quotient function. And obviously you can always place the extra restriction that the denominator has to be non-zero. We're going to talk about this in a little bit more detail in the coming slides, that why we place this extra restriction. But that's all. This is a simple example of how to add two functions, subtract two functions, multiply them, divide them. Now let's have one more example on the similar question. So you are given the fx, you are given a gx. So this is a linear function. This is a quadratic function. So just perform all the operations. So the first thing you have to find is f plus gx, which is, we know, fx plus gx. So fx is 3x minus 1 and gx is x squared plus 2. So you simply add them, combine like terms. So there's only one x squared term, there's only one x term, but there are two constants, minus 1 plus 2. Adding them up, you get plus 1. Then f minus gx is fx minus gx. Fx is 3x minus 1, gx is x squared plus 2. So now you do the subtraction, sign changes, minus x squared plus 3x minus 3. So combining the like terms again, f times g, what would that be? Fx times gx. Now fx is 3x minus 1, gx is x squared plus 2. So this time you have to do the multiplication of two binomials. And so multiply them. You can use FOIL technique or whatever technique you know how to multiply two algebraic expressions. So first 3x is multiplied with x squared, then 3x is multiplied with 2. Then minus is multiplied with x squared, and then minus is multiplied with 2. So 3x cubed plus 6 times x minus x squared minus 2. That's what you get as f times g, product function. And the last one is quotient function, where you simply divide them. Now fx is 3x minus 1, gx is x squared plus 2. Now there's nothing much to simplify about this quotient function because you do not see any factor cancellation. Anyways, we'll talk about even if there is a factor getting cancelled out, you don't need to. So just leave it here. That's the answer for this practice problem. Now that you know how to combine them and find all the 4 types of functions, let's move ahead to do function evaluation at specific points. Like these examples which we just talked about, you are simply evaluating sum difference product quotient of functions as functions. Your final answer was also a function of x. But now, instead of evaluating all these sum, product, difference and quotient as functions, you are supposed to evaluate them at specific points. So here are the examples. What do we mean by that? So this is the function given to us, fx, x squared minus 6x plus 8, and gx is x minus 2. Find each of the function values. So let's look at A, f minus g4. Now how do you simplify this? It's a difference function, so it would be f at 4 minus g at 4. Remember, f minus g at x is fx minus gx. The only difference is now you are given a specific value of x, which is x equals to 4. So the same definition gets applied. So f4 minus g4. Now you have to find f of 4 minus g4. You can now compute them separately and then plug in their values here, or you can do it here only. So I will do it separately. So what would be f of 4? 4 square minus 6 times 4 plus 8, which is 16 minus 24 plus 8. And how much is that? Actually, this is 0. So f of 4 is 0. And now what is g of 4? So use the definition of gx to evaluate g of 4. 4 minus 2 equals to 2. So 0 minus 2 is minus 2. So it's very simple. You evaluate individual function at the specified point and then plug in here whatever operation is being done in between them. So do the math, you get the answer. So this is negative 2. Now look at B. F over G evaluated at 3. So it would be F3 over G3, coming from the definition of the quotient function that it's fx divided by gx. So f3 over g3. Now again, we'll go back to the definitions of fx and gx and evaluate f3 and g3. So I'm going to write it here. fx is x squared minus 6x plus 8. So f3 is 3 squared minus 6 times 3 plus 8. So 9 minus 18 plus 8. So 17 minus 18, that's negative 1. So f of 3 is negative 1. And now you need to evaluate g3. So gx is x minus 2. So g3 is 3 minus 2, which is plus 1. So negative 1 divided by 1. So it's actually negative 1. That's B. Now the last one, f plus gx. Now this one does not give you a specific point, so you are only supposed to write your final answer in the form of function itself, means in the terms of x. So it's simply addition of the functions fx and gx. Now fx is x squared minus 6x plus 8, gx is x minus 2. Simplify, combine the like terms, only one x squared term. 2x terms, minus 6 plus 1 gives you minus 5x, 8 minus 2 gives you 6. So that's all about this example, where you also learned how to evaluate difference or product or quotient or sum at specific points. So it's essentially these 4 definitions which are always coming into practice. So the more you do these kind of examples, you'll better remember them. All right, now let's talk about domain of combined functions. In the past, we were already introduced with the concept of domain of a function. So let me recall you, what do we mean by domain of any function? So domain of a function f of x is all those real numbers for which the function is defined, well defined. Means if you plug in a specific value and the function becomes not defined, that means that point cannot be in the domain. So the domain is coming from the set of real numbers. It is all those real numbers which make the function well defined. Now you are working with two functions, fx and gx. So they will have their individual domains. So let domain of fx be, say, df, and let domain of another function gx is denoted by dg, because they are going to be sets. They are going to be in terms of intervals, basically subsets of real line. So let they be df and dg respectively. And now we are interested to know what is the domain of the new function f plus g, because combining functions, you are creating new functions. So those new functions are also going to have some domains. So we are interested to answer that question here. So what's the domain of f plus g, f minus g, fg, and f divided by g? Now this result is telling you all that piece of information in one sentence. That the domain of each of the new functions, new function means sum, difference, product, quotient. It consists of those values of x that are common to the domains of f and g. Common. Common means what? Intersection. So basically you have to take individual domains and take their intersection. That will be the new domain. Except that for f over g. For quotient function, you have to be a little extra careful. You also have to take into consideration that the points where the denominator is becoming 0 must be excluded. So in other words, what this result is telling you, so domain of f plus g is domain of f intersection domain of g. Domain of f intersection domain of g. Domain of f intersection domain of g. Again, domain of f intersection domain of g, and intersection with those x where gx is not equals to 0. So in other words, where gx is becoming 0, that has to be excluded. So if you remember this result, it will be very easy to understand the domains of the new functions which you are creating. I'll give you an example to understand this. Okay, here we have an example, but before doing that example, I'll give you another simple example. Say you have fx equals to x square and gx equals to maybe, say, square root of x. Now domain of f is all reals. It's the whole real line. In terms of interval, it's negative infinity to infinity. And domain of g is, if you remember, we have done this function, it's a square root function. So x cannot be negative. So domain of g is actually 0 to infinity. Only non-negative values are allowed. So what would be the domain of f plus g? The domain of f plus g is intersection. So what's the common part? Now domain of f is the whole real line, right? And the domain of g only starts from 0 onwards. So obviously 0 onwards, that's the intersection part in both the domains. So d of f plus g is actually this. D of f minus g is also the same. And in fact, domain of f times g is also the same. This is coming from this result that you just have to take intersection of individual domains, you get the output. But when you write domain of f over g, then this is the intersection of individual domains and intersection with those values where g is non-zero. Now look at g function. It is not allowed to be 0. Now at what number it is becoming 0? It's becoming 0 at x equals to 0. So that means 0 has to be excluded. So actually it turns out to be this interval 0 to infinity, the same interval but excluding 0. So that's the basic understanding of how to find domains of newly combined functions. Obviously for this you should be good at individually finding domains of individual functions and then taking the intersections. If you are good with that, you'll be able to do this. So here we have one more example, finding domains of combined functions. So we'll combine for all 4 functions. So let's first find those functions. So f plus gx is 2x minus 1 plus square root x. F minus g is 2x minus 1 minus square root x. F times gx is 2x minus 1 multiplied with square root of x, and f divided by gx is 2x minus 1 divided by square root of x. Now, before writing the domains of combined functions, let's first write domain of individual functions. So what's the domain of f? It's actually all reals. Remember, this is a linear function, straight line. So straight line is defined everywhere. Whatever value you substitute for x, this is a well-defined function. So domain of this is all reals. Domain of g is 0 to infinity. Square root function, so its domain is only the non-negative reals. So it's similar to actually the kind of example we just did. So domain of f plus g, domain of f minus g, and domain of f times g is actually, they are all same. They are intersection of this, which is 0 to infinity. You just have to write a different answer for domain of the quotient function. So that's 0 to infinity and intersection with x, which makes gx non-zero. So now this denominator is going to become 0 at x equals to 0. So you have to exclude that point. So this has to be open interval 0 to infinity, similar to the example we just did. All right, so that's about finding the domain of combined functions. And now let's talk about another type of combination of functions. You learned about 4 techniques, 4 different ways of combining functions: sum, difference, product, quotient. Now this is a 5th way of combining functions, which is not one of the fundamental algebraic operations. We do not do this operation with numbers. This is exclusively done only for functions. So let's first try to understand its meaning and then many other things about it. This is known as composition of functions. It's a very important concept in algebra and it has applications in calculus as well. So it's important for you to understand this. All right. So go back to the understanding of the function. When we defined function, remember we introduced the analogy of a function with like a machine to which you are giving something as an input and expecting something as an output. And usually input is the variable x, the independent variable x, and output is a function of x. That could be x squared, that could be x plus 1, that could be x cubed minus x, anything. Whatever you are doing with x, that's your function. Now imagine doing this 2 times. Like there are 2 machines. First you start from x, so that's the first input. So put it into the first machine defined by gx equals to x squared minus 1. So that's what your output is going to look like after you pass it through the first function g of x. And now this output, make it the input of the second machine or the second function, which is root x. So now when you input this to this machine, then what do you get? Square root of x squared minus 1. Because remember how this function is working? Look at how this function is working. That whatever you are giving to this as input, it is going to take the same thing and put it inside the square root. That's the understanding of how fx equals to square root x work. That whatever you give to this as an input in place for x, it's going to take its square root. So now instead of x, you are inputting x square minus 1. So f will take square root of that. So output is square root of x square minus 1. So function of a function. First you apply one function and then on the output you apply another function, gives you a third function. So this function is known as composition function of gx and fx. One of that function was this, another function was this. So this is composition of that, right? And now we have a notation to understand this. For composition, we got a notation. Just like sum, product, difference, and quotient, they got their symbols, plus, minus, dot, and division. Here we have a particular symbol to denote that this is a composition. This symbol is O, F-O-G-X. It's also read like this. In fact, this is, you can say, the definition of the composition. It's f of g of x. That first on x, you are using the definition of g. Then whatever you get as an output of g, that you are using as an input to the function f. So from x, you go to gx, and then from gx, you feed that gx to another function f as an input. So that's how you create composition functions, and this is read as f of g of x. And now let's do some examples to understand it. Okay, before doing the example, we do have a notation, or I would say terminology associated with it. This becomes very handy if you rename, or you can say remember f and g in terms of inner and outer function. And it's very easy. There's nothing hard to remember about it. So see, f of g is defined as f of gx. Now gx is known as the inner function and fx is known as the outer function. Now remember when we were talking about sum, I told you that f plus g is same as g plus f. F minus g is of course different than g minus f. So in addition, it doesn't really matter whether you do f plus g or g plus f, but in subtraction, if I say subtract these two functions, then I have to tell you the order, whether I'm looking for f minus g or g minus f, because they are different. Similarly, in composition, when I ask you compose these two functions, the order has to be specified. Which function I want to operate first, which function is the inner function and which function is the outer function. So that's how it is decided. The function which gets operated first on x is the inner function, and then the function which gets operated after is the outer function. So to evaluate f of gx, we must evaluate the inner function g at x and then use the result gx as the input for the outer function. So let's now do some example. So you are given fx equals to x cubed, gx equals to x plus 1, find each composite function value. So here we are actually constructing the composition of function, but instead of first finding the function, we are only evaluating it at a specific point. So let's first learn that. F O G, I want to evaluate it at a specific point 1. So if you go by the definition of f o g x, it is f of gx. That first you use g and then you use f. So it is f of g1. Now I need to have g1. So in the definition of gx, you used to replace x with 1. That's how you do function evaluation. So what is g1? 1 plus 1, 2. So I'm going to replace this here because g1 is 2. Now I have to compute f of 2. So f of 2 is 2 cube, which is 8. So this is 8. So that's how you get f of g at 1 equals to 8. And now try to compute g of f at 1. So if you get g of f at 1, so this would require you to first compute f of 1. So now f of 1 is going to be 1 cube, which is 1. and now you use the definition of G to evaluate it at 1. So what is G of 1? We have already found it, that's 2. So this is 2. So you see how it's being operated. Here you first use G's definition on this X value, then feed it to F. Here you first used F definition to evaluate it and then feed it to G. That's the whole thing. If you understand this thing, you understand composition. And now you can even compare that this is 8 and this is 2. So f of G actually is not equals to G of F. The thing which I was telling you about, that the sum is same, product is same, but difference and quotient, they are different if you switch the order of F and G. Similar with composition, f of G in general is never equals to G of F. Right? Let's go ahead to more examples. Here also we have to find composition of functions at specific points. You are given fx is 2x plus 1, you are given gx is 2x square minus 3. So to evaluate this, f of g at 2, f g 2. So first evaluate g of 2. So I'm going to write it here, gx is 2x square minus 3. What is g of 2? 2 times 2 square minus 3. So 2 times 4 minus 3. So 8 minus 3, that is 5. So g of 2 is 5. Replace that here. And now you need to evaluate f at 5. fx is 2x plus 1. So f at 5 is 2 times 5 plus 1. 10 plus 1 equals to 11. So that's it. That's the first answer. Let's find g of f2. So first you want f at 2. So what would be f at 2? Use the definition of f. 2 times 2 plus 1, that's 5. And now you evaluate g at 5. So g at 5 is 2 times 5 square minus 3. 5 square is 25 times 2 is 50 minus 3, that's 47. So that's the answer. f of g at 0, f g at 0. Now this is again the definition of g. So what is g at 0? Minus 3. And now what is f of minus 3? Very easy to find. 2 times minus 3 plus 1 minus 7 plus 1 minus 6. G of f at 1 over 2. So let's first compute f of half. So this is the definition of fx. F of half is 2 times 1 half plus 1. 1 plus 1 equals to 2. And you find now g of 2. G of 2 is something you already found in the beginning, 5. So these are all the answers of these 4 different questions. So with this, you can practice more questions in the textbook. So these are very easy, evaluating composition functions at a specified point. So now let's go ahead and talk about domain of composition of function. Because we talked about domain of sum, product, difference and quotient, we learned that domain of those 4 kind of combination of functions was nothing but, what was the result about the domain if I show you that again? Yeah, so domain was simply intersection of the domains of individual functions, and for quotient you had to have additional restriction that the denominator cannot be 0. Now it's not similar for composition of functions. To find domain of composition of functions, let's see how we process this through examples. You will understand this through examples. So I would want you to practice this on examples and understand it in your own words or in your own process instead of trying to memorize what this sentence is going to say. Let f and g be 2 functions. The domain of composite functions f of g consists of those values of x in the domain of g for which gx is in the domain of f. In other words, what we are trying to say here is that when you are talking about this function, since this is how it works, so first x has to be in the domain of G, because if x is not in the domain of G, then how would you apply the function's G definition here, right? Because on the variable x, G gets applied first. So x has to be in the domain of G. That's where it comes from, that x in the domain of G. And then, other than that, more important than that is, I would say, whatever you get after evaluating G at x means this number, because this is going to be some number. This Gx has to be in the domain of f. So Gx is in the domain of f. So those values of x which satisfies both these two conditions, that it's also in the domain of G, and after finding G there, whatever you get is also in the domain of f, those values of x are going to be in the domain of f of G, because these are the two conditions. If both of them are satisfied, only then the function is going to be well defined. So let's now apply these two examples, and you will see it very easy to find the domain from the examples. So here we have now example number 1 on finding the domains. So first we have to find functions, and then we have to find their domains. Earlier examples focused on finding the composition of functions but at specific points. But now we have to evaluate composition of functions in general. See, how do you know? Because when nothing is mentioned, right? So you are not given any specific point here. So that means we are talking about f of G at a general x. So we have to evaluate f of G x. In other words, it's f of Gx. Now first the definition of G gets applied. So you rewrite f as f, you retain f as f, and replace the function's definition Gx here as an input to f. So wherever you see Gx, use the definition of Gx and substitute it here. This is inside the parentheses of f. And now look at the function f. What the function f is doing. If you're feeding x as an input to function f, it is taking the square root of x minus 2. So now imagine this as x, which you are feeding to f. Now function's f definition is x minus 2. Now instead of x, you have a square root of 4 minus x here. So square root of 4 minus x minus 2. So what just happened here is, basically f of Gx is going to look like fx. It's basically the outer function fx, x minus 2. Instead of x, what will be there? Gx. So finding f of Gx is nothing but the definition of f function, but instead of x, you have as an input there as Gx. So fx was square root x minus 2. Now if I ask you replace x with Gx in the definition of fx, what would you get? Square root of x minus 2. Now instead of x, what you have? Square root of 4 minus x. So that's what gets added up here, and that's what you get as a function f of Gx. Alright, so if you understand the first example, we should be good to do the next one, g of x. Now g of x is basically g of fx, means it's a composition of same two functions but in the different order. So in this case, you first apply the definition of f first. So g is the outer function, f is the inner function, so fx is a square root x minus 2 coming from here. And now you use the definition of g. Now the definition of Gx is a square root of 4 minus x. Now in the definition of g, you replace x with square root of x minus 2. So this is what you get as g of f. So you can clearly compare them and see they are not same. F of h. So f of hx. Now first use the definition of h. H is x square And now use the definition of f, which is square root of x minus 2. Instead of x, you have x square. So x square minus 2. G of hx. So first the definition of hx, which is x square. Then the definition of g, which is square root of 4 minus x. Instead of x, we have x square. Hog. So h of gx. And now the definition of gx is a square root 4 minus x, and the definition of h is x square. So instead of x, we have square root of 4 minus x. So square of that, 1 second. And so you get square root of 4 minus x square. So square and square root cancel each other. So you get 4 minus x. So this is what the function evaluations are, and now we have to talk about their domains. So let's talk about all of their domains one by one. So first function was fogx. See, this was the function square root of 4 minus x minus 2. Now if I tell you this technique, if I recall you this technique, what was the statement saying? This statement was saying that whatever is the inner function, first you have to find domain of that function, and then you have to choose those values of x which make this well defined. Now how to do that in the example? So there are two ways. You could process it from the evaluated function, or you could just process it from the individual functions. So let's see what we get. Fx is square root x minus 2 and gx is square root 4 minus x. So gx being the inner function, let's first find domain of gx. Now domain of g. So we know that how to find, we have learned this in the past, how to find domain of any square root function. So whatever you see inside the square root, that has to be non-negative. So when you do that, you get an interval x less than equals to 4. That's the domain of g. In terms of interval, this is negative infinity to 4 ending at 4 including 4. And now if you look at this function, the outer function, because now you don't have to find domain of fx, you have to actually find domain of fogx, because that's our main function. So for this function to be well defined, because this is also a square root function, we know how does the domain finding works for a square root function, that whatever you see inside the square root, that has to be non-negative. See, whatever you see inside the square root, so this whole expression gets moved here and you put that in terms of an inequality, that has to be greater than equals to 0. So your task is to solve this inequality. Now this is where your knowledge on solving inequalities will come to practice, and it will help you finding the domain. So when you try to solve this inequality, so you square this one up, because to get rid of square root, you square both sides. So this is what you get. 4 minus x is greater than equals to 4, which gives you, if you subtract 4 from both sides, so you get minus x greater than equals to 0, or x is less than or equals to 0. You will flip the inequality sign when you try to get rid of minus here by multiplying both sides with a negative sign, equivalent to say that. So this is the domain of FOG. Now this has to be taken intersection with this. Now this is the process. First you find domain of G, then you find domain of the outer function FOG, and then take the intersection. Now what's the intersection of both of these? Because this in terms of an interval is negative infinity to 0. So on the real line you have 0, you have 4. So domain of G was going all the way up to 4, while domain of the outer function is telling you going all the way up to 0. So clearly this is the intersection going all the way up to 0. So finally I should be able to write domain of FOGX should be negative infinity to 0. So let's do one more example from that list, G of fx. So g of x, this function was here square root of 4 minus square root of x minus 2. Square root of 4 minus square root of x minus 2. Now this time inner function is fx. So we have to find the domain of the inner function. Now fx is square root of x minus 2. So what is domain of inner function? Same process, square root function, whatever is inside the square root that has to be greater than equals to 0. Solve the inequality. You'll get an interval. This time you get the interval 2 to infinity because x is greater than equals to 2. So domain of f is 2 to infinity. Now you find domain of the outer function because this is also a square root function. So for that, whatever you see inside the square root, this whole thing, that has to be non-negative. So you take the whole thing, put that greater than equals to 0 and solve the inequality. So you can move the square root term on the other side, and now to get rid of the square root you square both sides. So 16 is greater than equals to x minus 2. So add 2. So 16 plus 2 is greater than equals to x. So 18 is greater than equals to x, or in other words x is less than equals to 18. So in terms of interval, that is negative infinity to 18. So domain of g of f is the intersection of domain of f and what you just found, negative infinity to 18. So if you process that on the real line, so 2 to infinity, that's one interval. Another interval is negative infinity to 18. That's another interval. So clearly the intersection part is this much, 2 to 18. So this is an interval 2 to 18. Greater than 2, less than 18. So that's what you will get, both closed intervals, because the endpoints are included. So this is different than FOG, because here you first have to find domain of f first, inner function is f, and then outer function. So see, everything depends on how fundamentally you are clear about finding individual domains and then combining that piece of information here. So that's how you find domains. So we can do maybe all of them. Yeah, just give me a second. Yeah, let's do the third one. We'll do all of them. C is FOH, square root x square minus 2. So FOH function is square root x square minus 2. Now for this function, finding the domain of this function, first find domain of inner function, which is just x square. Now x square, the domain of that is all reals, minus infinity to infinity. And to find domain of FOH, we need to interpret the outer function. The outer function is a square root function. So x square minus 2 has to be greater than equals to 0. Same thing, whatever you see inside the square root has to be non-negative. Solve that. You can take the square root. When you take the square root, this is what you would get. Square root of x square is greater than equals to square root 2. And now square root of x square is absolute value of x. So remember that, if you forget it, because I have told you in the past, square root of x square is just not equals to x, it's equals to absolute value of x. So that gives you an inequality, but it's absolute value inequality, which breaks down further as greater than equals to 2 or x less than equals to minus square root 2. So you need to go back and revise how an absolute value inequality works. So you'll remember this. So this is what you get as a domain of this function, outer function. Now to finally write domain of FOH, you have to take intersection of this with the domain of the inner function, which is the whole real line. So whenever you are taking intersection with the whole real line, so it's actually this only, because that's the only common part, because this has no additional restrictions. So the only restrictions will be coming from here. So that's the final answer. That is the domain of this function. You want to write in the form of an interval, so you can do that. Negative infinity to negative square root 2. union square root 2 to infinity, because we know about this type of answers. We have done this kind of questions before. When you express them in intervals, this is how they turn out to be, union of two different intervals. All right, let's do the next one. D, GOH. Now you can pause the video and try doing that yourself and then confirm, validate your answers later. So G of H is square root 4 minus x square. So G of Hx is square root 4 minus x square. Now inner function is hx, which is x square. We know the domain of that is all reals, negative infinity to infinity, so it won't affect anything. That means whatever you get as the domain of this function, that would be the final answer. So treat it like just a function, find its domain. Same thing, whatever you see inside the square root should be non-negative. Simplify that. So you get 4 is greater than equals to x square. Take the square root. Square root of 4 is 2. Square root of x square is again absolute value of x. So this is absolute value of x less than equals to 2. This is different than this situation. This was a greater than absolute value inequality. This is a less than it type absolute value inequality. The answer for this is minus 2 is less than equals to x is less than equals to 2. So here your final answer is the domain of G of Hx is the closed interval negative 2 to 2. And then we have the last one, HOG, which is simply 4 minus x. Now we can do that here only. HOGX is 4 minus x. Inner function is gx. Gx is the square root 4 minus x. Domain of G is, we have already found it, negative infinity to 4. And then domain of HOG will be intersection of what you get as the domain of this function. Now this is simply a linear function, straight line. Its domain is whole real line. So its whole real line means negative infinity to infinity, intersection with negative infinity to 4. So it is negative infinity to 4. Because you take intersection of anything with the real line, it is itself. So that's the final answer. That's the domain of HOG. So these are a little lengthier. You need to be very good at finding individual domains and then learn the additional steps. So work on more examples for this topic to understand it better. So this is a remark about composition of functions. We already saw that FOG in general is not equals to G of F. And now another skill we want to learn about function is decomposing a function. We just learned how to combine functions to create new functions, specifically the composition. But now it's the reverse process. You are given a function in decomposed form, you have to break it down into individual functions. So let's learn that through an example, how to do that. So I'm going to rewrite this example. The solution is there on the next slide, but I want to first write it down here. That's the function which is given to you, and the question says write the given function hx as FOGX. That means your task is to write this function as a composition of two simpler functions. So if you want to do that, so in other words, they are trying to say identify the outer function and identify the inner function. So you understand this is the reverse of what we were doing. Earlier we were given f and g, we were composing them to create a new function. Now we are given the function in the combined form, we have to break it down to two individual functions. So let's see how we do that. So h of x is 1 over square root 2x squared plus 1. So in the entire function expression, so try to find a function which is identifiable. So you can see 2x squared plus 1, this whole thing can be a function. This is a well-defined function. So take that expression and name that equals to an inner function, because usually the notation for inner function is g if you're trying to write it as FOG. So this whole thing is g of x. And now go back to hx. So this is 1 over square root 2x square plus 1, which is 1 over square root gx. Now you want to write h of x as f of gx. So this is what you get. F of gx is 1 over square root of gx. Now from here, if I want to deduce what should be f of x, so it's very clear to identify that. It's very easy to identify that. Wherever is gx, you replace that with x. You know, we were doing the opposite thing earlier, that in the definition of fx you replace x with gx. Now you have to do the opposite. In the definition of the outer function, wherever you identified that gx, because it was you who identified that I would name this as gx, you replace that with x and you get your outer function. So f of x is 1 over square root of x. So we have found the answer. H of x is actually f of gx, where fx is 1 over square root of x and gx is 2x square plus 1. If you want to confirm your answer, you can again take composition of those two functions. You should get back the original function. So this is the same thing is explained here in step-by-step process, that whenever you want to write h as a composite of simpler functions f and g such that this, then define gx as any expression in the defining equation for h. So that's the defining equation for h. So find out the expression which looks like a function to you and call it gx. And then to get fx, what you have to do is you replace hx with fx and you replace this with x. Replace gx with x. That's what I told you. And this is the validation part. The third step is verification part, that you again take the composition of f and g. You should get back the original function. So that will be a confirmation that you have done it all correct. Now there could be other choices as well for f and g. It's not like it's always unique decomposition, but whatever works for you, like whatever strikes you. For example, you can try this. If you would have chosen gx as 2x square, that instead of whole of it to be chosen as gx, if you would have only chosen dx as 2x square, and fx would have been then 1 over square root x plus 1. So you try this one as well. That would work. So this is the process of decomposition. Now let's practice this on more example. So here we have the same question. You are given a composed function. We want to rewrite it as f o g x. We want to find what is fx and what is gx. So first identify the inner function. So in the whole of the definition of hx, you take one expression containing x and call it gx. So I'm going to call 2x plus 3 as g of x. And then h of x is 5 over gx, and h you want to write as f o g. So this is 5 over gx, and f of gx is 5 over gx. So f of x is 5 over x. So in the outer function, in the given function, you replace gx with x, you will get f of x. So it's 5 over x, right? So you get, final answer is fx is 5 over x and gx is 2x plus 3. Now if you want to do the verification, you can actually again try to compose f with g and see what you get. So first use the definition of g, which is 2x plus 3, and then use the definition of f, which is 5 over x. Instead of x, it should be 2x plus 3, which is same as h of x, and hence verified. So that's the process of decomposition. One more example and then we are all done with this topic. So I want you to try this yourself. You can pause the video and try doing this on your own and then come back and verify the answer. Alright, now let's do the verification. So one single expression, call it gx, x square minus 7. So hx is cube root of gx, and now hx is fogx, so that's cube root of gx. So f of gx is cube root of gx. So what should be f of x? Cube root of x. So that's the verification. That's your fx and that's your gx. You could also rewrite this as x to the power 1/3, but that's not necessary. You could leave it there only. And then you can also do the verification. Fog, first use the definition of g, which is x square minus 7. Then use the definition of f, which is taking the cube root of whatever you feed to it. So this is same as h of x. So hence verified. So that's all about this lecture. You learned various ways of combining functions, addition, subtraction, multiplication, division, how to find domains of all those combination of functions, how to evaluate them at specific points, how to evaluate them in general. And then we talked about composition of functions, domain of composition of functions, evaluating composition of functions at specific points and in general. And then we talked about decomposing a function. So these skills are going to be immensely useful in pre-calculus and calculus. So that's all for today. Practice more questions.